Hello everyone, welcome to video 21. The topic of this video is going to be series and sigma notation, and this will be your final video for the 2019-2020 school year in this pre-calculus class and this distance learning. After this video, if you have not already, make sure to look at the assessment choice board to decide on how you'd like to assess on each objective. For this one, I think the problems can be kind of interesting because they're very puzzly in nature. So I'd also encourage to do the project assessment for series and sigma notation. But again, that's not a requirement. You can do the other two options if you prefer. All right, so for this video, the objectives are to investigate arithmetic and geometric series. So if I take the sequences from the previous video and add each term, how can we go through and solve that? Learn about sigma notation, and then can an infinite series have a finite sum? So it's this kind of idea here of almost like a paradox. And we're not going to explore this in the video today, just because of material, and it's just one thing that we're going to kind of cut out to simplify everything that we're looking at during this whole environment. And so there is a question on the project assessment that kind of deals with this idea in terms of a basketball, a racquetball, or whatever kind of ball you want to think about being dropped off of a roof and counting how far it travels in between every single bounce. And so it's this idea that if the ball was to bounce infinitely, if it never stopped, is there a finite distance it could travel? And so that kind of explores that, and that's what that question is kind of centered around without actually saying it. So a lot of the words that are thrown around right now is this word, this idea of a series, this idea of a sum. So let's go through and define that. So when the terms of a sequence are summed, we call it a series. That's really kind of the basic definition for this. So recall that a sequence is just an ordered list of quantities, of numbers, of objects, etc. So if I was to go through and add up each of the individual terms of that sequence, then what that is called is a series. And there's a lot of nuances with series that you get into when it comes to a Cal 2 class. You spend an entire unit in a Calculus BC as well as a Calculus 2, a second semester course, college course in calculus on it, which is why we're going to look at some series. And then sigma notation again will be used in Cal 1 towards the later half of that class, which is why I wanted to make sure we looked at it this year. So let's start with the basics and really just kind of look again at what a series is. So let's start with a problem that a teacher gave to a child mathematician by the name of Gauss. Gauss is a really famous mathematician for specific math fields. He created an algorithm, etc., for matrices to help solve systems of equations. He also came up with this really kind of nifty way to solve this problem. Gauss was in school. His teacher, the joke that I like to kind of make up and tell is the teacher was tired of teaching, so the teacher gave a problem that the students would work on for a long time, and the teacher could take a break and grade or do whatever they wanted to do. And so what the teacher gave to them was to add up or sum the first 100 whole numbers. So in other words, 1 plus 2 plus 3 plus 4 plus 5, all the way out to 96 plus 97 plus 98 plus 99 plus 100, and to spend the class time doing that. And Gauss, again, came from the age where there were no calculators, there was no paper. They were really writing on slabs of slate. So it was almost like miniature chalkboards. And so even just trying to add up all of these numbers would have taken forever to go through and do. And even using a calculator, like you would sit there and have to, it would take a while to kind of add up these numbers. And so what Gauss did, though, is a couple minutes after the teacher sat down, after assigning the problem, Gauss came up with a slate board and gave his solution, and his solution was accurate. So he solved this problem in probably less than 5 minutes. And so that's kind of our task right now. And the task that I want to give to you right now is how did he do it? Like what technique, what would the sum S of this be without having to go through and add up every single individual number? So I'd encourage you to pause the video here and see if you can figure it out. What kind of creative ways could you go through? And then continue. Don't pause if you just want to kind of hear what he did. Okay, so what Gauss did was very, very, very creative. He ended up going through and he recognized a pattern where if he took the first number and added it with the last number, he got 101. Then if he took the next number and added it with the second to last number, he got 101. And then he would continue this process, adding each number with that number to the last. And he did this pairing up every single number till he got down to 25 plus 26 is equal to 101. So in other words, by pairing up these two numbers, the sum came out to be the same. And he even really didn't even need to go down to this final step here, because we know that in this list there are 100 numbers. And so if I go through and I pair up and I add just two numbers together to get the same number here, how many pairs would there be? And so he said the same thing. He said, okay, well, if there's 100 numbers and I'm pairing them all up, that means there are going to be 50 pairs of these 101. And instead of having to add up the numbers 1 to 100 individually, I can go through and say that this is 101 times 100 divided by 2, or 101 times 50, because there are 50 101s. And this math is much easier to calculate. I did the wrong work on the page. That's okay. This comes out to be 50. And so this is the sum. I realized in my lesson plans I wrote adding up the numbers to 100, but I did it to 50, which is kind of funny. So this 25 to 26, you're probably like, why is that 101? It's because it's not. I had the wrong problem in my head. So this would go to 50 plus 51, but there would still be 50 pairs, etc. So I'll make that correction in my PDF that I post to go with this. But this is what Gus ended up doing. He ended up finding the sum to be 5,050 by creatively going through and pairing up these numbers in order to find the sum. Now, if you're looking at this series right here, 1 plus 2 plus 3 plus 4 plus 5, recognize that this is an arithmetic sequence. Right? There is a common difference between each term. Therefore, we call this an arithmetic series. So because we're adding up the terms in an arithmetic sequence, we call this an arithmetic series. And when we go through and deal with these arithmetic series, series in general as well can either be finite. In other words, they terminate in terms of the number of terms I have, or they can be infinite series. Now, for the scope of this class, we generally do go into infinite. We're not going to go into that just because, again, of the timing and kind of where we're at. But in Cal 2, you will investigate this a little bit more, this idea of adding up an infinite number of terms, because you would imagine if you continue to add numbers that you would never actually sum up to anything, but that's not exactly true. There are cases where you can add infinitely many times and you will converge to a specific sum, which is really, really interesting because it's very paradoxical. And so we got finite or infinite. So let's take a look at an example and let's see, well, there's the wording right there. That's what I was kind of looking for. Let's take a look at this example here and let's see if we can apply what Gauss did to see if it helps us in a different style of sum. And here again, notice that this is an arithmetic series specifically. The common difference is 4. We can see that by going from 7 to 11 and then 11 to 15, etc., all the way up to 91. So Gauss, again, what he did is he said, okay, well, let's pair up the first and last numbers. So 7 plus 91 is 98. Then he went through and said, okay, well, let's pair up the next two numbers. So 11 and 87, again, is 98. And we would need to do this until we get to essentially the middle. But we don't know where that middle is because I don't know how many terms there are. Right? How many numbers are there here? And so we need to go through and figure that out, because when we had it from 1 to 100, it was really easy because we could just say, 1 to 100 is 100 numbers, so we could divide by 2. But here it's not as clear since we're not adding by 1. It's not like a one-to-one kind of counting. And so it's a little bit more difficult. But the idea that this is arithmetic plays a huge role now because of how we know these terms interact. Because it's an arithmetic sequence, we can figure out what term number 91 is using one of the formulas from the previous video. And so we know that for an arithmetic sequence, that the nth term is equal to the common difference times n minus 1 plus the first term, a1. And so in our problem here, we actually know all of these pieces, right? I want to know what is the 91st term. So I know 91 has to be equal to 4 times n, which I don't know what that is, plus 7. And we can go through and solve for n. So I can subtract 7, so this would be 84 is equal to 4 n minus 1. I can divide by 4 and get 21 is equal to n minus 1, or n is equal to 2, or 22, sorry. And so this tells me that there are 22 terms. So I know that if I go through and I pair up these numbers and I get 98, that there are going to be 22 divided by 2 pairs, or 11 98s. And so I can go through now and say that the sum is going to be equal to 98 times 22 divided by 2, which is 11. So the sum is 1078. All right, and so this example here really kind of conveys two formulas that we can use for arithmetic series in order to find the sum without actually adding up every individual number. All right, and those two formulas are given below. So given an arithmetic series, a1 plus a2 plus a3 all the way to an, then the sum is determined by the first term plus the last term. So notice that's exactly what we were doing beforehand, figuring out what is the pairs, what's that sum, and then n divided by 2, right? So how many terms are there? And because I'm pairing them up, I cut that in half. And so this can find me the sum of any arithmetic series with the fact that the last term there, whatever that nth term is, can be found by doing the common difference times n minus 1 plus a1. So it gives me a way to solve for the number of terms if it's not clear how many terms there are, because we definitely don't want to go through and have to count all of those terms and try to list all of that out. All right, so in example 2, we're going to go through and essentially use these formulas just kind of in a different way. All right, and so an arithmetic series has 55 terms, a first term of 85, and a sum of negative 11,066. What is the last term of the series? All right, so let's just kind of go through and label what I'm told. So I'm told that there are 55 terms. So n is equal to 55. I'm told that the first term is 85, so I know a1 is 85. I know that the sum is negative 11,066. And what I'm looking for is a of 55. I want to know what is the last term of the series. Okay, and so what we can do is we can turn and look at the formula for the sum. So S is equal to A1 plus AN times N all over 2. And notice how I know everything but that last term, so I can just plug in what I know. So the sum is negative 11,066, has to be equal to 85 plus A 55 times 55 divided by 2. And now I can solve for the missing term here. I can multiply by 2 to get negative 22,132. This is equal to 85 plus that 55th term times 55. Divide 55 on both sides. I would get negative 402.4. This is equal to 85 plus A 55. Subtract 85, and we get that last term. Has to be negative 487.4. All All right, so in the project assessment, you're going to see some questions that kind of deal like in this type of problem where you know pieces and you have to use the formula to find the remaining pieces. So it's a little bit more of a puzzle and really kind of seeing how you understand the formulas and the terms. All right, so that's it for arithmetic series as far as what we're going to look at. Let's take a look at geometric, as you could probably see as I was kind of scrolling. So a geometric series, can we find a shortcut like we did with arithmetic? Is there a shortcut? So I've got an example here, and then we'll kind of define it generally. So I have S is equal to 1 plus 4 plus 16 plus 64 plus 256 plus 1024. Now, just as a reminder, a geometric series or a geometric sequence, because that's where these terms are coming from, is determined by a common ratio, right? So you start with a number and then you're multiplying by the same thing to get each entry in here. So if 1 is my starting term, to go from 1 to 4, I have multiplied by 4, multiplied by 4, by 4, by 4, by 4. And so in this problem, we can kind of see that my R is 4. And remember that we can find that by doing one entry divided by the previous entry. It's just another way to kind of find it a little bit easier. And this is true. 16 divided by 4, 64 divided by 16, all the way down the list. Now, this is really important because the shortcut is actually determined pretty creatively, I think. And it's a way that you wouldn't necessarily think about trying. And so it's a very kind of cool thing to see. The idea is that we're going to construct a new geometric series by essentially taking the one we have here, and I'm going to multiply it by an extra 4, right? That 4 again being what that ratio was. So if I go through and I multiply the series by 4, I'm going to go through and multiply each entry by 4. So I would get 4 times 1, 4 times 4, 4 times 16, 4 times 64, 4 times 256, and then 4 times 1024, which is 4096. And so you can almost see that by multiplying by 4, it's almost like a shift in the original series. Like we're looking at starting here and going, let me get my pen back, starting here and going to one extra term, which is the 4096. And what I'm going to do next is actually subtract these two lines. And I'm going to subtract them in terms of this order, 4s minus s. And so when I do the subtraction, 4s minus s, I'm taking everything in this list here, and I'm subtracting from it. I'm taking away everything in the original list. So anything that they have in common gets canceled out, right? That means I'm essentially saying 1024 minus 1024, 256 minus 256, all the way down until I'm really just left with two things, 4096 minus 1. Well, we can simplify that. That's just 4095. Now on the left-hand side, we can also simplify this, right? 4s minus s is just 3s. Right? I've got 4 s's, take one away. Well, if the whole question here is to solve for s, right? I'm trying to figure out what the sum is. Well, if I just divide by 3, I have s, right? 4095 divided by 3 is 1365. So by doing this kind of manipulation, we just found what the sum of the original series is. And you can check this. You can go back through and add up 1, 4, 16, 64, 256, and 1024, and you should get 1365. So the process that we just did worked. It was kind of weird, right? It just kind of happens all of a sudden. So let's take a look at essentially what's happening generically, and then we'll see this in an example. So in general, we know that a geometric sequence contains these terms, a, ar squared, all the way to ar to the n minus 1. Now, this is a geometric sequence, so to make it a series, we are adding every single term together. Now, if you remember from the process above, what I do is multiply the series by an extra r, so whatever that may be. And when I do that, it's going to essentially shift each term to the next power on r. it essentially gives me to the next piece. And then in our process, we went through and said, okay, well, let's subtract these two lines because that's going to get rid of a lot of the fluff. It gets rid of all the middle pieces. What it's going to leave me with is this extra term by multiplying by this r in the very first term in the sum. So I get ar to the n minus a. Well, when we were dealing this with numbers, we could actually subtract. Now here we can't really do that because I don't know what r is, because it's just a general expression. So instead, because these two pieces here have an Sn in common, I'm going to factor that Sn out. And so I have that the sum of the original series is equal to ar to the n minus a all over r minus 1. And so this says that for a geometric series, this formula here will find me the sum of that series, right? Where a is the very first term in the series, r is that common ratio, how each term is found. Now in terms of the parts, what I want you to really kind of see from this is that this ar to the n here is the extra term. A here is that first term that we were talking about. And notice how we're dividing by one less than the ratio. And that's exactly what we did here. We said, let's do 4095 divided by 3. And remember that 4095 came from getting that extra term, which was 4096, if I was to multiply by 4 one more time. And I subtracted from it the very first term in the series, which is 1. All right, so let's put this formula to use so you can kind of see and hear me kind of talk it out here in example 3. So compute the sum of each series, 1 plus 6 all the way out to 7, 7, 7, 6, and then B, 25 plus 10 all the way to plus 32, 1/25. So in A, we need to figure out what my R is. All right, so here it's kind of straightforward to see that my R is going to be 6. Right, we can do 6 divided by 1 or 36 divided by 6. Now, what's really interesting about a geometric is geometric doesn't care how many terms there are. Right? I don't need to know what n is, unlike arithmetic. Instead, I really just need to go through and figure out what would the extra term be. I need to multiply 776 by 6 one more time. So that would be 46,656. So a lot of sixes. And so what that tells me then is that A is 1, AR to the N is 46,656. And now I actually have everything to calculate the sum according to the formula. S is equal to AR to the N, so that extra term, 46, I keep wanting to put the 5 first, 656 minus 1, all over R minus 1. So I get 46,655 divided by 5, and so this sum comes out to be 9,331. And that's the answer to the geometric series. So we can do the same thing in B. Now here the R is a little bit harder to see. I'm going to move this stuff up so I can kind of leave the problem there. All right, so to find R, I remember one way to do that is to take a term and divide it by its previous term. So in this case, my R is 2/5 when I reduce that down, which I would encourage you to. So there's my R. If I was to go one extra term, if I multiply by another 2/5, I would get 64 over 625. And then my first term is 25. So now I can set up my formula for a geometric. The sum is going to be equal to that next term. So 64 over 625 minus the very first term, which is 25. And then I'm dividing this by 2/5 minus 1. 1 less than R. Now, working through this algebra, make sure that you're remembering that working with numbers here, you have to have a common denominator if you're doing this by hand. If you're to use a calculator, convert this over to a fraction, you should get 5187 over 125. This is my final sum. All right, and I'll leave it to you to work through that to get that as an exercise, because from here it's just kind of algebra. Okay, so that's geometric. It doesn't get much crazier than that. And so in the project assessment, again, you'll have some problems there where you can try to calculate and work through some geometric series. All right, and so that leaves us then with sigma notation. So let's talk about sigma notation. So sigma notation was invented and created as a way to shorthand or express a series in better shorthand, right? That's kind of the central idea. So whenever we are adding up multiple terms, I can express it as a single function using sigma notation. And again, collapse it into just one piece. And so in this example right here, to help show what sigma notation is, I've got essentially an arithmetic series or sequence if you're looking at the individual terms. And I want to go through and just again kind of recall some of the information that we talked about at the very beginning of this video, as well as in the previous video for arithmetic sequences. And that if I have an arithmetic sequence, I can express it as a function as an, that nth term is d n minus 1 plus a1. And so in this problem, if I wanted to go through and express each term as a function, I could do that. Each term is found by doing 2, because that's the common difference, times n minus 1 plus the first term, which is 2. All right, and then I could go through and simplify this, distribute the 2, so 2n minus 2 plus 2 is 0. So notice that it's essentially, each term is found by doing 2 times n, where n is 1, 2, 3, all the way out to 27 would be the final number that I would need to plug in, because 2 times 27 would give me 54. All right, so notice again that I could plug 54 in for an and solve for n like we've done before, and then I can figure out what my n is in terms of the number of terms there. Now here's what sigma notation does. So sigma notation takes this function, this expression that we just came up with for each term, and then it represents that we are adding by using the capital Greek letter sigma. So it looks like this. It's kind of got a little corner right there if you're not familiar with it. And so what it does is it takes this and says 2n, and then it writes it where it says n is going from 1 to 27. And so what this represents then is it represents that this is a series, so I'm adding up a bunch of terms where those terms are found by plugging into this expression. This expression represents the sequence, right? Each individual piece, where then sigma says you are adding up all those pieces. Now to get to those pieces, I'm using essentially my index, right? And as we do an index in sigma notation, the indices always increase by 1, right? Just like how we would normally count. 1, 2, 3, 4, no decimals or anything like this. So this would say plug in 1 plus plug in 2 plus plug in 3 plus plug in 4 plus, and I would go all the way out until I got to 27. I'd plug 27 in to get 54, and I know to stop there because that's what that top number represents. And so it's essentially almost like a lower limit, a lower bound to an upper bound, upper limit of what we're going to plug in. And again, it's counting here as we go. Look at it almost like a function. We're looking for those outputs, and then the sigma says to add up all of those outputs. And so this again is a shorthand way. It's a way to shorten all of this addition, since it's so repetitive, into a single function or expression. All right, and so the next example is really just going to kind of go through and work on how sigma notation expands. So it kind of gets you used to the individual pieces, and then we'll go the other direction. Given a series, can you write it in sigma notation? Okay, so example 4. So write each of the following sums in expanded form. So write out the series, and then we'll calculate the value of each sum. All right, so in A, we have sigma notation. So the sum from j is equal to 3 to 6 of 2 to the j. Now, I chose to write these problems this way and leave them this way because the variable doesn't matter, right? It's a dummy variable. It just tells you what you're plugging in and what you're using. You could call J X, you could call it T, you can call it N. It does not matter. It's essentially a placeholder, because what I'm going to do and what really matters is I'm going to plug in 3 for J, and then I'm going to plug in 4 for J, plus plug in 5, plus plug in 6. And I'm going to stop there because that's what the top number is. From here, I just need to go through and add up these numbers, right? 2 to the third is 8. 2 to the fourth is 16, plus 32, plus 64. And then either doing this by hand or using a calculator, you'll find the sum to be 120. That's it. That's sigma notation. All right, so in B, I have sigma, so the sum from n is equal to 3 to 5. And my expression, my function here, is 4n squared plus 2. Generally, they call this the argument, right? What you're arguing, your point, what we're plugging into. So in terms of the expansion, I'm going to plug in 3. So this would be 3 squared plus 2. Plus, now I'm going to plug in 4. Plus, now I'm going to plug in 5. And I'm going to stop there because that's what the upper limit is. Now I go through and I can simplify each parenthesis or add this all up at the same time. We get a sum of 206. In C, I want to find the sum from k is equal to 1 to 5, and my argument is 16 times 1/2 to the k. So see how it's 1/2? So that means I'm multiplying by 1/2 each time. So this is almost an example of a geometric. So I'm going to go through and I'm going to plug in 1. So I get 16 1/2 to the first, plus plug in 2, plus plug in 3, plus plug in 4. I wrote a 3 here. Plug in 5, and I stop here because that's what my upper limit is. Now I can use a calculator and actually figure out what is 16 times 1/2, 16 times 1/2 squared, all the way down, to get a sum of 15.5. All right, now for the final one, I want to find the sum of m is equal to 1 to 4, where my argument is 1 over m times m plus 1 in parentheses. So then this is going to be equal to, I'm going to plug in 1 for m. So this will be 1 over 1 times 1 plus 1, plus plug in 2, plus plug in 3, plus plug in 4, and I stop there because that's what the upper limit is. Going through and simplifying, this would come out to be 4/5, or 0.8. Now, your calculator does have a sigma notation feature. It's one I would encourage you to go ahead and look at now. You could go through and check these sums that way. If you were to go to math and then scroll down, what you should see is either the sigma notation on your graphing calculator, or it will say summation. All right, one of those two. And if you click that, it'll actually put in this Greek letter for sigma. And then it will allow you to pick a variable. I would generally just hit X and just use X for your inputs and things like that. And then you can type in your argument, make sure to close off your parentheses, etc., and hit enter, and it'll print out the sum for you. This is going to be really, really useful again when you get into calculus, because there will be at a time at the end of the class where you will be adding sequences, right? You're going to have a sequence of terms that sigma notation and using a calculator can shorthand it. And then it leads into one of the most important calculus concepts. Really, again, there wouldn't be calculus without it. And so sigma notation is going to be very, very important to understand and be able to work with before you get into AB calculus, at least at the end of that class. Okay, so the final example that I have for you then is essentially practicing for that. And it's really just going to be a short expression with this, a short example with this, because it's semi-straightforward. There's only so many ways to do it and practice with it. So example 5, express the following sums in sigma notation and then find the sum. So I have 3 plus 3.5 plus 4 plus 4.5 plus 5 plus 5.5. And then I have my example there for B. Now in A here, one of the first things that you should recognize is that this is arithmetic. Right? I know it's arithmetic because each term there is found by a common difference, right? I'm adding 0.5 each time. So my D is 0.5. Now that's relevant because I need to write my argument for this series, right? I need to know what AN is. And so I know then that because it's arithmetic, that it has to be D times n minus 1 plus the first term, which is 3. Here's my argument. To make this a little bit easier to use, we can simplify it. So I can distribute the 0.5. So this would be minus 0.5 plus 3 or plus 2.5. So this is the argument that I'm actually going to use for my sigma notation. So I have my sigma. N is going to start at 1. The question is what does it run to? What is the upper bound here? Because I know my argument, it's 0.5n plus 2.5. What I'm not sure of is what that last number should be, so that when I plug it in, it will give me or print me out the last number here. Now, we can easily count that, right? We can go through and just say 1, 2, 3, 4, 5, 6. But what if the series is so big that we know the last number, but I don't know how many terms are in between? So just to show you that, remember what this expression here that we just wrote, that argument means, right? It says that when I plug my n in, it should print me out each individual term, starting with 1, 2, 3, 4. So I can set that last term equal to my argument and then solve for n. And if you do that, subtracting 2.5, I get 3.0 is equal to 0.5n. You'll find that n is equal to 6, which is what we got just by counting. And there's my sigma notation. All right, we can find the sum by using a calculator or just going through and adding these terms. You get, let's see if I wrote it out, 25.5. We can also use what we talked about previously, that because it's an arithmetic series, we know this shortcut to doing that now. All right, B. Notice this is a geometric. So I'm showing you two very special, unique series here. In this geometric, notice that my R is 1 divided by 4. So I'm multiplying by 1/4 each time. And so that means if I wanted to write this as a specific example, remember that my AN is equal to AR to the n minus 1. This is my general expression. N goes from 1 to all the way out, and we're not sure how far it's going to go, so we need to figure that out. Now again, we could count, but just to show you how we could solve for something like that, we could go through and say that A is the first term, so AN is equal to 4. My R is 1/4 n minus 1. We could go through and solve for n by setting this equal to 1/16. So I get 1/4 n minus 1 is equal to, divide by 4, 1/32. And then we can use our exponent rules to go through and solve and say that n is equal to 4 here. So now my sigma notation, n is equal to 1, and we'll go to 4. My argument is 4, 1/4 to the n minus 1. Using our shortcuts or sigma notation, we can go through and add these numbers, and we get that the sum would be 81/16. And so this is sigma notation. For geometric, it's a little bit harder to write it out, I think, just because you have to be careful with your exponents. And so I kind of I took some liberties in terms of showing you that, because for now, that's not going to be one of the most important things you see. It's really just getting used to the argument and how we can do the indices for sigma notation. So that's it for this video. We've talked about arithmetic, geometric, how we can go through and use those shortcuts. So you'll be applying those to the problems on the project assessment. And then using sigma notation, we can use our calculator to do a little bit more shorthand and it's something, again, that you will see in calculus. So thank you for watching. Let me know if you have any questions, and we are almost there. Stay strong. I appreciate all of y'all's hard work. Thank you.